So in the previous video, we talked about how to add, subtract, and scale matrices, how to calculate the transpose of a matrix, and how to calculate the determinant of a relatively small square matrix. Today we're going to talk about how to multiply one matrix by another matrix. And this is going to be one of the most important matrix operations that we are going to be using over and over again throughout this entire course. Just like with matrix addition and matrix subtraction, if you want to multiply two matrices together, their sizes have to be compatible. However, if you want the matrices to be compatibly sized for multiplication, their sizes and shapes have to follow the following rule. If you're going to take a matrix A and multiply it by a matrix B, A times B, just like this, then matrix A, if it has n columns, matrix B has to have n rows. So these guys right here in the center have to be exactly the same. So this is what it means for two matrices to be compatibly sized for multiplication. And when we talk about the process for multiplying matrices, this condition is going to make sense why it's here. Okay, so to demonstrate the process, let me take, for example, the following matrix A, which has 2 rows and 3 columns. And I'll put in the top row the values -2, 0, 1, and in the second row the values 3, -1, +4. I'm going to define now a matrix B, which has 3 rows and 4 columns. So pretty hefty matrix here. In the first row, let's have 5, 0, 1, 2. In the second row, let's have 1, -1, 0, 0. And in the third row, let's go ahead and have 2, 1, -3, and then 1 again. So if possible, let's go ahead and multiply together in the order A first and then times B, A and then B. So the first thing I'm going to notice is that it is possible to multiply these matrices in the order of A first and B second, because they are compatibly sized for that kind of multiplication. The matrix A has 3 columns. The matrix B has 3 rows. So they are compatibly sized for that operation. So now that we've established that it is possible to calculate this product, let's go ahead and do so. So when we are multiplying together a 2 by 3 matrix and a 3 by 4 matrix, the result of this calculation is going to be 2 by 4. Essentially, when these two values in the middle match, these guys kind of just cancel out, and what results from that product is 2 by 4. So how do we find the entries of this 2 by 4 matrix that results from this calculation? I'll go ahead and set up the template over here, 2 rows and 4 columns. To find the very first entry of the resulting matrix, the entry in the first row and the first column, what I'm going to do is I'm going to consider the first row of matrix number 1 and the first column of matrix number 2. So to find entry in row 1 and column 1 of the result, we're going to calculate a dot product between row 1 of the first matrix and column 1 of the second matrix. So I'm going to take the dot product between this row and this column, which means that I'm going to calculate the product of -2 and 5. I'm going to calculate the product of 0 and 1. I'm going to calculate the product of 1 and 2. And I'm going to add all of those results together. So -2 times 5 plus 0 times 1 plus 1 times 1 times 2, which gives me a result of -10 plus 2, result -8. That -8 is going to be the value in row 1, column 1 of our resulting matrix. If I want to find the entry in row 1, column 2 of our resulting matrix, I'm going to dot product row 1 of the first matrix with column 2 of the second matrix. Is what we get by dotting row 1 of A with column 2 of B. So in this case, I would be dotting together this top row of A with this second column of B, and that's going to give me the entry in row 1, column 2 of my answer. So if I dot product the first row with the second column, I'll get -2 times 0, 0 times -1, 1 times +1, and if I add all of those values together, we'll get a result of +1 in that entry. So to find the entry in row 1, column 3 of our answer, I'm going to dot together row 1 of the first matrix with column 3 of the second matrix. So that's -2 times 1, 0 times 0, 1 times -3. So that's going to give us a result of -5 there. That final entry in the top row is going to be the dot product of this top row and this fourth column. So that's -2 times 2, 0, 0, 1, 1. So adding all of those products together gives us a -3. Now to build the second row of our result, we're going to dot product this second row of matrix A with the different columns of B. For example, that first dot product, 3 times 5, -1 times 1, 4 times 2, 22. Second row, second column, that dot product would be 0 plus 1 plus 4, result 5. Second row, third column, the dot product would be 3 plus 0 minus 12, so -9. And then finally, second row, fourth column, would give us 6 plus 0 plus 4, result 10. So this 2 by 4 matrix that we've constructed by calculating all of these dot products would be the result of the matrix multiplication A times B. And so this is the reason why, in order for it to be possible to multiply the matrices together, the number of columns of A has to match the number of rows of B. If this didn't match, then the dot products involved in the matrix multiplication would not be well defined, because when we dot product two things together, they have to be exactly the same number of entries. Now, let's consider what happens if they asked us to multiply these matrices in the opposite order, B times A. If we try to do a multiplication in the opposite order, where B is on the left and A is on the right, in this case, this is a matrix multiplication that cannot be completed, and it's not defined. There are two ways to see that at this point. First of all, the dimensions and size of the matrix B. B has 3 rows and 4 columns. Meanwhile, the matrix A has 2 rows and 3 columns. And so in this case, these two values in the center do not match. Because the two values in the center do not match, you know right away that the matrix multiplication that they're asking for in this case, with B on the left and A on the right, this multiplication is not defined. You can also see this when you write down this matrix product. This first dot product cannot be calculated. So our conclusion here would just be that this matrix product that you're asking for does not exist, and we're going to walk away from that calculation because it cannot be completed. Let's go ahead and do another demonstration with some matrices that are a little bit smaller. So for example, let's have a 2 by 2 matrix A, whose entries are 3, 4, -1, and 2. And let's have another 2 by 2 matrix B, whose entries are, let's say 0, 5, -2, and -3. So someone asks us to calculate the product A times B in that order. And the first thing that I'm going to note is that this product is possible because A and B are compatibly sized for that variety of multiplication. So now let's go ahead and follow through on that calculation. And let's go ahead and use dot products to calculate the result. Now, if I calculate the dot product of row 1 with column 1, then that's going to give me the entry in row 1, column 1 of my answer. So the dot product 3 times 0 plus 4 times -2 is going to give me, in the end, an entry of -8 in column 1, row 1. If I dot together the first row of A with the second column of B, that's going to give me the entry in row 1, column 2 of my answer. So that product would be 3 times 5 plus 4 times -3. So that's 15 minus 12. So that's +3. Then finding the dot product of the second row of A with the first column of B, that's going to give me the entry in the second row and the first column of my answer. So that's going to be -1 times 0, 2 times -2, and that's going to give me a result of -4. And then finally, I will dot together row 2 and column 2, and it'll give me the entry in row 2, column 2 of my answer. So -1 times 5 plus 2 times -3, that's -5 combined with -6, in total -11. So that is going to be the result of this matrix product. Let's do it again, but in the other order. This time putting matrix B first in the product and putting matrix A second in the product. In this case, reversing the order of the product still gives us a result that is compatible in its size, because again, a 2 by 2 matrix times another 2 by 2 matrix. There's a match here in these dimensions in the middle, starting with the dot product of row 1 and column 1. In this case, we get 0 times 3 and -1 times 5, result -5. Taking the dot product of row 1 and column 2, we get 0 plus 10, so that's 10. Taking the dot product of -2 minus 3 with 3 minus 1, that gives us -6, +3, in total -3. And then dot product of the second row with the second column, we get -8 minus 6, in total -14. So the major takeaway from these two examples that I really want you to note is that matrix multiplication is a lot like cross product and it's a lot like subtraction, where the order of the objects in the operation really does matter. Depending on whether A is first or B is first, you can get totally different results from your matrix product. Even more extreme, depending on the order of the matrices in your product, one of those results can be defined, and the other one in the opposite order might not even exist at all. So, something to be mindful of, major takeaway. A times B and B times A are usually totally different. So we will have to be very sensitive and attentive to the order of the matrices in our products when we're asked to calculate and work with matrix products. Now, just some final remarks. We noted that when we multiply two matrices together, if they're compatibly sized, if these entries match, then you can predict the size of the product pretty easily. These middle dimensions basically just cancel out and collapse in on themselves, and the resulting matrix has m rows and p columns. So the number of rows of A determines the number of rows in the result, and the number of columns of B determines the number of columns in the result. Let's go on a little side quest and talk about an application of matrix multiplication to encryption and encoding of messages. So this is a pretty old school encoding method called the Hill cipher. The Hill cipher is a means of encoding that uses matrix multiplication. So the scenario is that you have some message that you're trying to send securely. So let's just say that we have a really simple message here like hello world. So the first thing that we would do is we would take each letter in the message and we would map it onto a corresponding number. Like the letter A would be 1, the letter B would be 2, the letter C would be 3, the letter D would be 4, and so on. So start by translating each letter in the message into its corresponding numerical value. Then group the letters in the message into packets or groups. For example, suppose you decide to group the letters in your message into packets of 3. So hello world would become HEL, which would become the packet 8512. The next letters LOW would become the packet 121523. The message ORL would become the packet 151812. And then finally the letter D would become 4. And then that's the end of the message. So we would fill up the rest of the packet with 0. So now you want to create an encryption key. An encryption key is a means of encoding and decoding the message. And in theory, you and the person that you're communicating to are the only people who know what the key is, so that you can encode the message securely and that other person can decode the message securely using the key. But no one else should know the key so that no one else can decrypt your message. For the Hill cipher, your encryption key comes in the form of a 3 by 3 matrix if your packets of letters have 3 letters in them. If you've decided to make your packets of letters of a different size, like maybe 5 letters in a single packet, then your Hill cipher encryption key would be a 5 by 5 matrix. So the size of the matrix matches the number of letters that you've put into each of these packets in the previous step. So just for an example, suppose that I have decided that my encryption key for the Hill cipher is going to come in the form of this 3 by 3 matrix. I'm then going to take each of the packets of letters that I have created corresponding to my message, and I am going to multiply them by this encryption key. So for example, here is my encryption key 3 by 3 matrix, and I'm multiplying that by the first packet of letters, the vector 8, 5, 12, set up as a column vector. So now that I have gotten this numerical result from applying the encryption key to that packet of letters, I have gotten the values 180, 304, and 425. And we're going to take those values now and convert them back into letters. Using, again, a numerical mapping that A corresponds to 1, and it also corresponds to 27 and 53 and so on. B corresponds to 2 and to 28 and to 54 and so on, and that kind of thing. So using that kind of arithmetic, the encrypted packet 180, 304, 425 turns into the three letters Y, S, and J. So this would be the encryption of the first three letters of my message. HEL in hello world has become YSJ in the encrypted message. So in the Hill cipher, we use matrix multiplication to encrypt messages. So that's one application of matrix multiplication. So let's go back to when we introduced connectivity matrices in lesson number 4, where we talked about if we have a collection of nodes, maybe for example A, B, C, which are connected potentially by some links or pathways, then this network can be represented by a connectivity matrix that has 3 rows and 3 columns. So this matrix right now is telling me how I can get from one node directly to another node. But I am realizing that I can eventually get from A over to C if I take 2 paths, right? If I start at A and take one path to node B, and then I reroute from B to C, I can get from A to C via a path of length 2. So let's see how matrix multiplication and this connectivity matrix allows me to reach that conclusion. What I'm going to do to look for paths of length 2 in this network is I'm going to take this matrix and I am going to raise it to a power of 2. I'm going to square this matrix and I am going to multiply it by itself. Now, if I follow through on those calculations using the standard dot product process. Dot product mode activated. So let's see what's going on in this matrix where we have raised the matrix to a power of 2. If I look at the matrix after a power of 2 has been obtained, the ones and zeros have moved to different locations. Now, for example, there is an entry of 1 connecting column A and row C. And what this is communicating is that you can get from A to C via a path of length 2. You can get from A to C if you follow this path first and this path second. So raising the connectivity matrix to the second power allows you to see that path of length 2 between these two nodes. I see that there is a 1 in B's column and A's row, and that communicates that I can get from B back to A, again via a path of length 2, if I go by way of C, then to A. And I also see that there is a 1 connecting us from C to B. And again, that communicates that there's a path of length 2 that brings us from C to B. So raising our connectivity matrix to the second power and multiplying that matrix by itself gives us the paths of length 2. And if you want to detect paths of a larger length, you can do that by raising your connectivity matrix to different powers. For example, if you take your connectivity matrix to the power 3, that's paths of length 3, and that would allow you to detect, for example, that if you started at A and you wanted to go back to A, there's a path of length 3 that would allow you to do that, A to B to C, and then back to A. So matrix multiplication can be used with connectivity matrices to detect longer paths. Another side quest, matrix multiplication can be used to show how a physical scenario or system evolves over time. Suppose that we have a population of people or a certain animal, and they have two habitats or two cities or two towns that they are occupying. So let's call X sub n the population that lives in the first habitat on day n, and let's call Y sub n the population that lives in habitat 2, habitat B, on that same day, n. Now, some members of the population are going to migrate between these habitats. So let's suppose, for example, that every single day, 10% of the folks who live in the first habitat migrate over to the second habitat. And let's suppose that every day, 5% of the folks who live in the second habitat migrate back over to the first. If that's what's happening, then you can use those values to set up a recursive relationship to show how the populations in each habitat are growing over time. So for example, if you start out with xn people in habitat A, and if you start out with yn people in habitat B, then what is going on the next day? The next day, Habitat A will retain 90% of its previous population. It will retain 90% because 10% of those guys migrated over to the other habitat. Meanwhile, Habitat A will have gained some population members from the guys who migrated coming over from Habitat B. So 5% of the folks in Habitat B came over to Habitat A and are now contributing to that population. Simultaneously and similarly, we have the evolution in Habitat B. Habitat B is retaining 95% of its original population. So the population on the next day is 95% of what it was on the previous day. Meanwhile, Habitat B is also gaining 10% of the population from Habitat A because those are the guys who are coming over from Habitat A. So this system of equations tells us how the population in the two habitats is evolving from one day to the next. Systems of equations like this one can be represented in terms of a matrix multiplication. What you might be able to notice is that this result on the left side of the system is exactly the same thing that you would get if you multiplied together this matrix product, a 2 by 2 matrix corresponding to the coefficients in our system, and then that coefficient matrix is being multiplied together by this vector xn, yn. So for example, this row here containing 90% and 5%, if you dot it with this column vector xn, yn, the result of that dot product is an exact match to this first expression here in this first equation, 90% xn plus 5% of yn. In other words, if we want to measure the effect of a day on the evolution of these two habitats, that can be understood using left multiplication by this coefficient matrix of the different percents here. So if you want to understand, for example, what is going on with this population in 100 days, all you have to do is multiply by this percent matrix 100 times. So this is another application of matrix products. Okay, that concludes our talk about matrix multiplication. If two matrices are compatibly sized, you can multiply them together. To multiply two matrices together, you use dot products between the rows of the first matrix and the columns of the second matrix. Matrix products are heavily sensitive to the order of multiplication. So you can get completely different results depending on whether A is first and B is last, or B is first and A is last. So be careful about that. And some of the sort of quintessential applications of matrix multiplication are in message encryption, for example, the Hill cipher, as well as in measuring the evolution of systems over time.